So the next speaker is Cyrus Omar, who will be talking about totally live programming with Hazel, progress report on the overall project. And this is joint work with Andrew Blinn and David Moon, all at the University of Michigan.
That's where I was hanging out this past weekend, down in the south of Portugal. Hold on, I need to...
I feel like many of us have opened that map with Humberto Delgado Airport on it.
When you're ready.
Okay, there we go. Oh, no, still not quite. I need to have this be mirror. I am doing a live demo, so I need to see what's going on here. Okay, I think that's it. Cool. Okay, All right, so let me start by saying that the Hazel project, I have my PhD students Andrew and David listed here, but it is a big collaborative project. There are, at this point, I think maybe 60 contributors to the Hazel project. I couldn't list all their names here, but the demo that you're going to see is a big collaborative effort. Many of them are undergraduates at the University of Michigan in my lab, the Future Programming Lab. So this is really a summary of a lot of the work that we've been doing over the past several years. There isn't really new results here. If you've been to like all of the Hazel talks at all the conferences, you might have seen everything in this talk. I just wanted to kind of bring it together. So the motivation for Hazel is really that programming today is not just opening up Notepad and writing code, right? Programming is really assisted. It's kind of a collaboration between us, human programmers, and programming environments that offer a number of language services, okay? So everything from syntax highlighting to code completion to go-to definition, all of those things are language services. They rely on the semantics of the language to provide you services. You can see that there's all these extensions that are specific to different programming languages and VS Code here. And we want these things to be available at all times as we code. In fact, we want them to be available in particular in these situations where the code isn't complete, right? That we're still working on the code. And there's a problem here, right? So when we are designing a programming language or defining a programming language, if you're defining standard ML, you write a book and you give all the rules for the grammar and the type system and the operational semantics, and all those rules are sort of positive rules. They tell you when a program is well-formed, is well-typed, has a result. Right? But when we're actually writing code, that's not always the case. In fact, there's data to suggest that that's not even commonly the case when we're writing code. So you'll have transiently, or even sometimes for a long time, especially if you're a student, you might have a syntax error, okay? And that means that everything else is meaningless, right? You have to fix that error before anything else can happen. Any of these tools, these services that we rely on, require that not to be the case. And then even if you don't have a syntax error, if you have a type error, that means that you can't run the program, and so you won't be able to get any feedback even about the parts of the program that maybe are working correctly. This is particularly relevant. I'm sure we've all encountered situations in our coding lives where we make a change to a type definition, and that change is going to require a number of downstream changes to a number of different functions, and those changes are going to take maybe days to resolve, right? That whole time we can't run any of our unit tests. We can't actually demo the code. We have to pull up a different branch to show it to our friends. Right? And so this is a problem that isn't just transient, it's a problem that can persist for a long period of time. And then there might be runtime errors, sort of things that we didn't expect to happen at runtime that cause the program to, again, crash, right? We don't recover gracefully from these things. They typically just cause something catastrophic to happen. I also want to point out, I won't talk too much about it in this talk, this is kind of ongoing work, but another way a program can be incomplete is when there are merge conflicts, when we're collaborating with other humans or maybe AIs or something like that, right? Maybe we have some disagreement about what should be at a particular location in the code, and if we get a merge conflict, it looks like this is going to totally flummox our parser or our type checker. This is not going to make sense to any tooling downstream of that, and we have to resolve these things before we can move on. So this gap, we call this the gap problem, that there's these gaps in these services that we rely on to code, as we do normal things when we're writing code. And so a lot of the work that we've been doing in the Hazel project over the last several years is rooted in solving the gap problem. And one way to do that is by starting with the syntax bit by using a structure editor. Okay? And so this idea of a structure editor has been around for a long time. I'll show you some examples in a bit. But the idea is instead of leaving the program in an unparsable state, you insert holes in the right places, and then you allow that hole to be a part of your syntax, and then you have to just reason about programs with holes in them. Okay, so you can handle missing parts of your code with a hole. You can also handle erroneous parts of your code by sort of thinking of the hole as a membrane around the error, and I'll show you examples of that. And then once you have this sort of, once you've sort of eliminated this kind of parse error, then you have to think about the semantics. And so you have to develop semantics that understands holes. And a lot of the papers that we've been writing over the past several years have focused on this problem of semantics for holes, with the goal of this sort of totally live programming experience, where there are really no editor states left that are syntactically, statically, or dynamically undefined. There's no undefined behavior. It's defined in some way. It handles it, and ideally handles it gracefully. This Friday at UPSLA, we'll have a paper on pattern matching with holes. How do you reason about exhaustiveness and redundancy checking when you have holes and patterns? And how do you run a program that has holes and patterns? So that's this Friday. We have a couple of other papers that I'll talk about here. And so a lot of the effort in the Hazel project has been taking this idea of total liveness, turning it into meta theory, and then proving theorems about it. So this is a key theorem from our POPL 2017 paper. You don't need to understand all the notation here, but the idea here is you can define a semantics not just for your operational semantics, but for your editor semantics. And so that's what this, let me see if I can, am I loud enough here? Is there a mic? Okay. Okay, so I just want to point at some things here. So this judgment here is a transition system for edit actions. Okay, so you're taking an editor state and transitioning it to another editor state, and typing is preserved by that transition system. And so that means that you never have statically undefined editor states. And this is a theorem that we've proven in AGDA, right? So we have a lot of good theory for that. That doesn't mean that every editor action that you want to perform is well defined. So at a paper that's coming up at POPL in January, we have another theorem that says, in fact, you can take any editor state and mark it with errors, with holes in the right places, so that every action that you want to take can be performed. So we have a number of things like this related to operational semantics. So all of these papers here are available to check that out. And so, you know, problem solved, right? Someone commented about this is UPSLA, so it's not POPL. Well, we got one UPSLA paper now, so problem solved. Well, the problem's not solved, okay? So you know, if you just use all of this theory, you end up with action semantics for which the usability questions are really kind of unclear. In fact, if you use the system in POPL 2017 and try to code, you're going to have a bad time. It's going to be really much less productive, despite this total liveness, than it would be to just use something like VS Code. So it's not just about solving it's necessary to solve the gap problem, but there's another problem that comes up whenever you start involving structure editing, whenever you start needing to insert holes. And we call that the viscosity problem. Oh, sorry, this was a joke that I forgot to do. It's a cat joke, so I'll do it. If you don't want to think about the theorems, the way to think about this part of the problem space is if your cat runs across your keyboard, most programming languages won't understand. You know, APL excluded maybe. And with Hazel, when you solve the gap problem, it will understand what your cat says. Okay? Okay, maybe that's a strong claim. I'm not sure. Okay, so Structure editors. Maybe many of you or many of you have people in your lives that have used a structure editor. How many of you have used Scratch? Okay. Yeah, when I do this in my undergraduate class, almost everybody learned programming using Scratch at this point, if they're undergraduate CS majors. Like it.
Linux 81 represent.
Yes. I didn't hear that, but yes. So how many of you would like to use Scratch for your day-to-day programming in your research careers? Okay, so there's some problem here, right? Scratch doesn't have the gap problem, but it has some other usability problem, right? It has this viscosity problem, we call it. And the problem here is, you know, it might be relatively straightforward to construct a program if you already have it in your head by dragging the blocks in and out. That's a little bit inefficient without a keyboard-driven interface. But once you have a big enough program like this, right, it becomes really hard to imagine restructuring this thing in an efficient way because you have to kind of like do tree rotations and transformations and pull things out into Scratch space and rotate around the blocks, right? And so a text editor is just a much more usable interface for writing large-scale programs. Okay, well, there are other structure editors. For example, JetBrains MPS is a really great example. This is a structure editor generator. So here's just an example of a editor written in MPS. So you can see down here what's happening is as you kind of insert code, you type the dot and there's a hole, and then you fill the hole and you keep going. And so this is much more productive. You can drive this with your keyboard. And this could also solve the gap problem, right? It has these holes, and so you get semantics using the work that we've talked about before, and then you're happy. Well, this actually works really great because of a number of heuristics that MPS has about code insertion into empty holes. But this problem of modifying or restructuring existing code still throws people for a loop. So there's some data from a study by Berger et al. In 2016. This is a little hard to read, but the idea here is if you talk about insertion, people really like, both experts and novices to MPS are sort of happy with the insertion interface. But with deletion and selection, and let me just talk about those. With those two operations, actually, there's a lot of unhappiness. And the reason for that is it's still, although it looks like a text editor, everything is projected into a textual view, it is still a tree editor at heart. So when you delete, for example, the plus between 2 and 2, you're deleting the entire plus node, or one of the plus node plus one of its children, and you're just leaving one side or the other. And so people perceive this as an inaccuracy in how deletion works. Even experts perceive this as an inaccuracy relative to text editing. So these two dots are not here, that's text editing, and that's novices and experts. Okay? Selection also is tree-oriented, and so when you select something, it selects more than, you have this kind of spooky action at a distance where you mean to select something right next to your cursor and it selects this whole big thing. And sometimes that can actually be helpful because you're often operating at the level of the big thing. But other times for certain kinds of restructurings that I'll show you, that's really not what you want. Okay? So the fundamental issue, another way to think about this fundamental issue is the affordances that you get as a user suggest that it's a text editor. The way it looks, the way the keyboard handles, suggests that it's a text editor, but it's really still a tree editor, and nearby things in the projection, in the textual projection, are not nearby to each other in the tree in all cases. Right? So if you think about like 2 times 3 plus 4, the 3 and the plus are adjacent to one another in the textual projection, but there's like a parenting relationship that goes up a couple of levels to actually get from the 3 to the plus. And that can be arbitrarily deep. So you get what I like to call spooky action at a distance here. Okay? So we did a study I'll talk about in a bit, but here's some quotes from, we compared some of what we're going to show you with MPS, and one student said, MPS was extremely cognitively demanding to me. It felt like I was solving tree manipulating puzzles the entire time I used it. The worst part by far is the lack of Scratch workspace. I think that comes from using Scratch where you can drag things into the margins. And several people, I think unprompted, mentioned Towers of Hanoi as what it felt like to work with MPS. Okay. If you're not familiar with Towers of Hanoi, it's like a little puzzle game where you have to like move things around by like putting things in the temporary Scratch space, and it's like a lot of tree rotation stuff. Okay, and maybe you could get used to that, right? And there's some data to suggest that if you like get used to this, if you spend enough time learning this, maybe you can get productive with it. There are industry users of MPS. Okay, so this is a very cool project. pretty ambitious project, but I think there are still some problems there. And so to get back to the problem, so solving the gap problem is critical, but so is solving the viscosity problem, the human aspects of this. And so what I want to show you in our demo is some of the work we've been doing specifically on that in the new version of Hazel, and the sort of terminology that we're using here is this idea of gradual structure editing. So where the structure is sort of, you can gradually destructure the structure and really get a much more textual manipulation of the program, rather than having to think with tree transformations. But there is always still a tree. And you can, in fact, use the tree transformations if that's the most natural thing for you to do. But you can destructure things gradually as needed. So it's kind of similar in spirit to maybe gradual typing, if you're familiar with that idea, where you can like choose whether to put type annotations. You can choose whether to work in a structural or destructured way. So let me pull up the demo. Put this down somewhere. Okay. I'll take it. Thanks. Okay, so Hazel is a web-based editor. So you can go to hazel.org and play with it if you want. When you open up Hazel, there's a few different modes. I'm going to just show you Scratch mode for a minute, but there's an exercises mode that students use that I'll show you in a moment as well. So Hazel is a live functional programming environment. So when you start in this mode, you get a cell that contains a single expression, and it's an empty cell. But in fact, it's not empty. In fact, it sort of has something in it that it represents emptiness. It's a hole. Okay, and if you look closely at this hole, it's a little hexagon. And even the cursor next to the hexagon is pointed to indicate this is like a convex hexagon. The left and right tips are convex, okay? And that'll become important in terms of developing intuition here. So anyway, I can fill the hole. If I fill it with a number like this, you can see what's happening is it's operating like a little calculator. So if I type in a number, it's evaluating it as I type. Okay, I'm not hitting enter, I'm not hitting run. It's a live environment. It's running code as I edit. Now, so what happens if I type times here? So you can see, although it was, I pressed space and then times, so it feels like a text editor, but what happened was, after the times, it didn't just leave it in a parse error sort of state, it inserted another hole, a hexagon there, and so that means there's not a parse error, right, because that hole is part of the syntax. And so now I just have to fill that hole, and if I fill it with 2, I get the result 6, as one would expect. If I delete it, I get the hole back again. Okay, so all hole management is automatic in Hazel. You don't have to ever manually insert a hole. Okay, cool. If I go over here and I delete the times, what would happen in other structure editors would be you would delete the entire times node, right? Or maybe you would delete all but one child. Which one do you leave behind? I don't know. It's like asking what who your favorite child is. That's an arbitrary question, right? There's no good answer to that. So here, you're not left with one child or the other. You're left with a different kind of hole. This is an operator hole, and you can see it's also a hexagon, but it's a concave hexagon to indicate that it's an operator. And so there's this hexagonalization metaphor that's really critical to understanding this, where like an expression is a convex hexagon, and to insert holes, what you have to do is make it a hexagon again. So if I like just left 2 and then plus here, without that hole there, it would be not a convex hexagon because the right side of the plus is concave, and so you insert this hole to make the pieces fit together, just like kind of a block editor, but you end up with the overall shape being a hexagon, convex hexagon. Okay, so that's what's happening here, and the same idea here. If you put 2 convex things together, you have to put something concave to glue them together, and that's the hexagonalization kind of Lego metaphor here. All right. Now, if I press plus, again, you get a hole on the other side, but now you observe something maybe slightly interesting is, although there's a hole here, the runtime system does not sort of crash when it sees the hole. It's not like arrays unimplemented or something like that. It's running the code as far as it can. It's doing the 2 times 3, and then it's saying, well, I don't know what to add to the 6, so I'm going to kind of leave it at that. And it's also it's a pure language, so you can kind of reorder things or skip over things as you wish. So you can go over here. You can set white space up as you want, by the way. It skips over the hole. It does the 3 times 4. It tells you you're adding 6 and 12, and then leaves the hole in the middle. We don't get so aggressive as to apply algebraic rewritings or anything here. I mean, that would be non-deterministic, right? Is it 18 plus hole or hole plus 18? Okay, so So you get this, you get this automatic management and also this sort of like live evaluation even in the presence of holes. So I've shown you empty holes. These are empty holes. You can also have non-empty holes. So if I put X here, excuse the multiple rendering of the error box here, but so that's the standard sort of error that a compiler would give you. You can even see it down here at the bottom. Oops. X not found, right? So that variable reference was not found. Normally, that would have the gap problem. So you try to put this through a compiler, it tells you that error, and then it waits for you to fix it before it can execute this code. Here, although it is a static type error, all the complaints about static typing preventing kind of like exploratory programming are alleviated here. Well, maybe not all of them, but many of them, because you're still running the program. It's just like propagating the static error to runtime and treating it like a whole. So it prevents the addition operations here from proceeding because there's no number to add, but it shows you that what you're trying to do is add something to 6, not just to 2 times 3. Okay, so hopefully you're getting the idea there. If I put true here, you'd get the type error, bool inconsistent with expected type int, but you would still get an execution with an error in the result. Okay, so that's one aspect of it. I've only shown you kind of simple arithmetic so far, so what about more complicated syntactic features? So the Hazel language is a typed functional language. It has algebraic data types, pattern matching, a module system, so it has all this fun stuff, but that requires fun syntax. And so what happens if I want to, for example, bind this expression that I'm still working on to a variable? So I'm going to write a let expression. I can just start typing let. When I press space, what it does is it doesn't actually try to fully structure the code. So this is the gradual destructuring I'm talking about. Okay, so it says, okay, you're trying to insert a let, but I don't actually know if you want this existing expression to be the bound expression or the body of this let. Do you want this to be bound to X or to be the place you use X? And so what it says is, well, I'm waiting for you to first name a variable like X, and then to type equals. Okay, and that equals could go here, in which case I've bound X to this variable, and then it says I'm waiting for you to type in to tell me where you want the in to go. And the in could really go anywhere here, right? But probably we want it over here. So I can go over here and either type in or press tab to autocomplete. And now I've returned structure to this program. But I could have gone the other way. So instead of putting the equals in the in here, or sorry, the in here, I could just put the in down here. And then what have I done? I've said I'm going to bind a variable X. I haven't told you what it is yet, but I'm going to be able to use it in this expression. So that was a choice that we had to make when we sort of wrapped the existing code in a let expression. And that could have been like 2 different tree actions determine, you know, that which action you invoke determines where the existing code ends up in the subtrees of the new form. But here, it feels much more like text editing. In fact, it feels almost like assisted text editing, where it reminds you of your syntactic obligations as you're typing. And this is actually really great, and I'll talk about our experience in the classroom in a moment. It's really great for students that are not familiar with functional programming and have never seen the let in construct, right? Maybe they're familiar with semicolons ending the let, and semicolon has a different meaning in this language. But you know, those kinds of errors, we believe, and we're still doing all the data analysis, we believe that those kinds of errors are reduced by this syntactic assistance that's provided here. Now, what we don't do, you might notice in this state, is I made this bold claim that every editor state in Hazel is meaningful, but you see this question mark at the bottom for the evaluation result. So this is ongoing work. Basically, when something's in the backpack, it's like there's something destructured about the state, and so it's hard to evaluate in this destructured state. But what you can do is sort of heuristically place the in a place following the same kind of logic that a error-correcting parser might use. But where an error-correcting parser only has the ability to sort of delete lines and insert tokens, we have the ability to also use holes to figure out where these things should go. And because the previous state was well-typed and well-formed and runnable, we could even use other heuristics, right? We could determine sort of like what do we think the user's doing, and that might allow us to play, or where do you think the user's going? Well, we know they're probably not trying to insert a type error, so maybe insert it in a place that minimizes type errors. So we're working on all that. I don't have a demo to show you of that right now, but maybe in a week or 2 I will. So anyway, so that's the basic idea. So now let me show you a demo of what it looks like from the perspective of a student doing an assignment. Okay, so we have this exercises mode. I'm just going to show you a really simple exercise where we're supposed to write the odd function as a recursive function. And so we have this kind of notebook-like interface for students to work through, and we use this very test-driven methodology. So what you get is a problem specification, with some equational stuff. You get a prelude, and this is just a read-only buffer, but it's still structured, okay? So you can go, you might have noticed that there are these syntactic hints that tell you about how the system is parsing this code, okay? So that colon is connecting the not variable. You can even see down here a description of what the variable, it says variable binding, it tells you its type. This thing is an arrow type, the equals is connected to the let and the in, okay? And then the fun down here is connected to the next line, but stops before the in. Right, so if you're new to functional programming, if you haven't seen this kind of syntax, it's going to be unfamiliar. You're not going to know how to kind of parenthesize things in the right way in your head, and so this kind of takes that operation you have to learn how to do in your mind, puts it up on the screen for you. So you can explore this, you get type feedback, right? You can say that this thing's expected type is bool, etc. All right, cool. Let me show you the student-facing view. So we have an instructor view as well for creating these exercises. But the student sees the type signature of the correct implementation of odd, and then what they're asked to do is write some tests against the correct implementation to make sure they understand the problem specification before they actually go in and solve the problem. Okay? And so what I can do is do some live testing as well. So if I type the test keyword, what it's asking for is a test here. So for example, odd of 0. Notice when I press open parentheses to do a function application, it doesn't close the function application. It just gives me the syntactic obligation that I need to close the parens. And then there's also an end keyword at the end of our test syntax. And then as soon as I finish that, before hitting run, before starting the test runner and switching to another window and seeing the result, you just get this little red X. And so maybe you caught the problem, maybe you didn't. 0 is not odd, 0 is even, right? Yep. So I can say not odd here, immediately get that feedback that that's a valid test, and I start getting points as well. So you get that instant gratification of now I'm not like at 0 points out of the problem, I have some points. We also do some mutation testing, so we have some hidden buggy implementations, so you can't just write a bunch of tests that test the same thing, you have to find the bugs. Then you write your implementation, so let me just do this really fast. If n equals 0, then true, else whole. So I'll leave the else branch, the recursive case, unspecified, but then I'll just go down here. There's some syntactic requirements that we test for as well. And it runs the same test that you wrote above. You can edit them either here or there. And you get feedback about, did your function pass this test? And nope, you wrote the base case wrong. So you can go back up here, change this to false. And then you can see that your test now passed. Okay, so students are quite happy with this. So let me just wrap up here with some summary data for you. Okay, so I won't go into what this shows, but it shows you basically that this is as productive as text editing for people in a lab study, and more productive than MPS. Okay, there's a paper at VLACC that was presented a couple weeks ago that has this data in it. We also did this fun heat map of sort of like if you give people code modification tasks, in a text editor, they reuse a lot of what's already been written and just kind of move things around. The heat map looks very similar for our editor, which we call the Tyler editor compared to VS Code. It looks very different from MPS, where people end up kind of deleting more than they wanted to and then rewriting it. Okay, so teaching with Hazel, we use it in an undergraduate PL class, which introduces FP for the first time to most students. 200 plus students have used Hazel at this point to complete multi-hour coding tasks. And notably, the tutorial that we give them is about what I just told you, even a kind of more condensed version of what I just told you. A 5-minute tutorial on how to edit in Hazel, then we say use your text editing intuitions, and students feel that this is a very easy to learn editor, by far the most user-friendly IDE editor I've ever used, the color designs are off, etc. Okay, so very, very nice comment. I'm cherry picking, obviously, but generally people like this. Okay, so big picture, the Hazel project is really about solving both the foundational PL problems, the semantics of holes, as well as the HCI problems, taking that really seriously. We're increasingly doing some AI stuff I didn't have a chance to talk about. And we want to use this to enable ambitious applications. So I talked about EdTech, but we are also interested in formal reasoning assistance for proof assistance, computational science applications, really taking collaboration seriously and ultimately building a live collaborative commons. So think of a computational Wikipedia where every page is a module and every element on the page is a programming construct. We really need that to be live. We don't want some editor somewhere in another time zone to go to sleep or have some coffee, and that breaks the whole system, right? So liveness is really important there, and we're building the foundations for that. So I'd be happy to talk about any of this stuff all week, and I'll take questions if we have time. Thanks.
Super. Yes, we are definitely short on time, but we can take a question and then maybe another one or two as we switch over to the next presentation.
Thanks for the talk, Cyrus. I had a question about how this interacts with sort of other programming language features. So I was thinking, how your live editing. So a lot of programming. You mentioned that it was pure. So what about sort of would these same techniques work for something that's mutable with kind of imperative features,
Yeah.
And also things like language features such as macros and such? Have you considered how that kind of might interact with your system? Thank you. Yeah.
Yeah, so the editor itself, the whole driven editor, you can definitely have that editor for an imperative language or for Prolog or whatever, right? The live evaluation features are much trickier to do in a setting with side effects just because you are running the program on every edit, so you don't necessarily want to spin off a network request or tell the robot to move on every key press, right? And so you have to have managed side effects, so I think something monadic might help there. And then just briefly on the macro system front, I didn't get a chance to show it, but we have this system of what are called live literals. There's a paper, PLDI 21. It's a graphical macro system. So because it's a structure editor, it doesn't have to be text. I just focused on text here. But it can be basically a graphical macro that uses the live data to show you kind of previews of things, but then generates code underneath. And so you can integrate GUIs and code, and it's compositional sub-expressions inside the GUIs. So happy to give a demo to anyone that's interested in that after the talk.
Okay, I think we're out of time, so let's save the questions for the break, the remaining questions for the break, but thank you, Cyrus, again.